Hi, Doctor. We are from Group 3. We'll be presenting our group assignment, and the topic that was chosen by us is smart surfaces, designing materials with self-cleaning and anti-fouling properties.
Smart spaces have become a burgeoning field in the material science, focusing on the development of materials with self-cleaning and anti-fouling properties. These surfaces have broad applications across various industries, including medical devices, marine vessels, and architectural surfaces. The main objective of these surfaces is to maintain functionality and aesthetic without frequent cleaning or maintenance. This assignment delves into the types of materials used for smart surfaces, exploring their structures, physical and mechanical properties, microscopic characteristics, processing methods, and design limitations, thereby highlighting their potential and limitations in advanced applications.
So I will be presenting about the detail on the type of materials that was chosen by us, which is titanium dioxide. So titanium dioxide is actually an organic compound and a semiconductor material, which also uh, a transition metal oxide, which exhibits unique properties suitable for various applications in engineering. So there are two primary crystalline forms distinguished by their crystal structures and properties, which are anatase and rutile. As for anatase, it has properties of high photocatalytic activity, making it effective in generating reactive oxygen species ROS under UV light. So these properties made it ideal for self-cleaning and antimicrobial applications such as coating for glass surface and others. As for rutile, it has a higher refractive index, which commonly used in pigments, sunscreen, and optical coatings due to its excellent light scattering and ultraviolet absorption capabilities. Next, um, this titanium dioxide can be engineered into various morphologies and applications to tailor its properties for specific applications. The first one is nanoparticles. Uh, it has a high surface area to volume ratio, which enhance the photocatalytic activity, and the applications are photovoltaics, photocatalysis, and environmental remediation. As for the thin films, it is commonly used in solar cells, sensors, and gas sensors due to its transparency, conductivity, and catalytic properties. And the last one is coating. It is applied to diverse materials, such as metals, ceramic, and polymers, which impart self-cleaning, anti-fouling, and antimicrobial properties. And it is commonly used in industries such as constructions, marine, healthcare, and automotive.
So hi, I'm going to explain about details on the physical properties of the materials. So for the titanium dioxide has several important physical properties that make it useful for a variety of application. It is a white, odorless powder that is very stable and non-reactive under normal conditions. There are two main crystalline forms of titanium dioxide: anatase and rutile. Anatase has a high ability to generate reactive oxygen species when exposed to UV light, which help break down organic material and kills bacteria, making it good for self-cleaning and antimicrobial uses. Rutile, on the other hand, is very good at scattering light and observing UV ray, which is why it's often used in sunscreen and paints. So that's all for me. Thank you.
Hi, hi, Assalamualaikum. My name is Danish Azri bin Yusaini. So today I will present to you about details on the mechanical properties of titanium dioxide. So mechanical properties of titanium dioxide are crucial in determining its stability for different applications, such especially in structural and also protective coating. So these properties include hardness, fracture toughness, high elastic modulus, and high compressive strength. So titanium dioxide exhibit a high hardness, which make it resistant to wear and abrasion, and it's varies depending on its crystalline form. With rutile having a higher hardness than anethys and brucite. So the next one, titanium dioxide have low fracture toughness. So titanium dioxide can be brittle and prone to cracking under stress. This property is influenced by its microstructure with polycrystalline form exhibiting different toughness level based on grain size and phase distribution. So the next one, titanium dioxide have high elastic modulus, which is mean it is measured of its stiffness and resistant to elastic deformation. Rutile titanium dioxide has an elastic modulus about 230 gigapascal, which is higher than that of many other ceramic material. So the next one is high compressive strength. Titanium dioxide exhibit high compressive strength, which is beneficial for its use in structural component and coating. The compressive strength of rutile titanium dioxide can exceed 1 gigapascal, indicating its ability to withstand significant loads without deformation. So the next one is details on microstructure of titanium dioxide. There are three types of microstructure, which is rutile, anatase, and brucite. So the microstructure of titanium dioxide significantly influence its mechanical properties and also overall performance. So it can be exist in several polymorphic form with anatase, rutile, and brucite, as I said just now, by being which is being the most common things. So rutile is the most thermodynamically stable form of titanium dioxide at high temperature. It has a tetragonal crystal structure with a high packing density, contributing to its hardness and stability. So the next one is anatase, which is a metastable form of titanium dioxide with a tetragonal crystal structure. It is less dense than rutile and has different optical and photocatalytic properties. And the next one is brucite. Brucite is the least common and least stable form of titanium dioxide. It has an orthorhombic crystal structure and is typically found in natural mineral deposit. So brucite's unique properties are less well studied compared to rutile and anatase, but it is of interest of certain specialized applications. So the next one is discussion on fabrication method, application of the material. So the fabrication method, there are four type of fabrication method, which is sol gel process, hydrothermal method, CVD method, and electrospinning. So sol gel method is a versatile and widely used technique for producing titanium dioxide nanoparticle. And this process involves the hydrolysis and condensation of titanium alkoxide in an alcoholic solution, forming a colloidal suspension, which is known as sol, that gradually evolve into a network, which is known as gel. So the gel is then dry and calcined to produce the titanium dioxide powder. So this method allows precise control over the particle size, crystallinity, and morphology of the titanium dioxide produced. And the next one is hydrothermal method. The hydrothermal method involves crystallizing titanium dioxide from aqueous solution at high temperature and pressure. And this technique enables the synthesis of titanium dioxide with specific crystal phase, which has the three phase, anatase, rutile, or brucite, and morphologies such as nanorods, nanowires, or nanotubes. And the next one is CVD method. CVD method or known as chemical vapor deposition. So titanium containing precursor are vaporized and then reacted with oxygen to form titanium dioxide thin film on various substrates. Sorry. This method is particularly useful for producing uniform and adherent coating of titanium dioxide on complex surfaces. CVD is widely used in the semiconductor industry for fabricating titanium dioxide thin film with control thickness and composition. So the next one is electrospinning. Electrospinning is employed to fabricate titanium dioxide nanofiber by applying a high voltage to a polymer solution containing a titanium precursor. The resulting nanofiber are collected on a grounded surface and subsequently calcined to remove the polymer matrix, leaving behind pure titanium dioxide fiber. Uh, so the next one is application of material of the material, which is titanium dioxide. And titanium dioxide, in the field of cosmetic and skincare, titanium dioxide is valued for its ability to scatter light, providing effective UV protection in sunscreen without causing any skin or irritation. So the next one is the photocatalytic properties find in uh, find in titanium dioxide for the environmental remediation, where titanium dioxide can break down organic pollutants and purify water and air when exposed to ultraviolet light. In food and also pharmaceutical industry, titanium dioxide serves as a safe additive, enhancing product appearance and stability. And in energy production, where titanium dioxide nanoparticles are explored for their potential in solar cells to improve efficiency, which are titanium dioxide is a known nanoparticles where titanium dioxide have uh, higher thermal conductivity. So the solar radiation that been absorbed to the plate will cool down by titanium dioxide nanoparticle or nanofluids in order to reduce the temperature to its operating temperature.
In summary, smart spaces with self-cleaning and anti-fouling properties are a significant advancement in materials science, addressing the needs for maintenance-free functionality and aesthetic preservation across various industries. Titanium dioxide, with its unique crystalline forms, versatile morphologies, and exceptional physical and mechanical properties, stands out as a pivotal material in this domain. Titanium dioxide's photocatalytic activity, hydrophilicity, and mechanical robustness are leveraged in a multitude of applications, from self-cleaning glass and antimicrobial coatings to pigments, sunscreens, and advanced electronic devices. The Soldier process, hydrothermal synthesis, chemical vapor depositions, and electrospinning are some of the key fabrication methods that allow precise control over titanium dioxide's properties, ensuring its adaptability for high-performance uses.